Assalamu alaikum. This video inshallah will be the part 3 of tutorial 2. It will be about nozzles and diffusers. Here we have an air. We will treat it as an ideal gas. In a nozzle is like this. That is how you represent a nozzle. The function or the purpose of the nozzle is to increase the velocity. So you will have a big cross-section area, then it will be reduced until the exit. So by decreasing the cross-sectional area, you will increase the velocity of the exit. The opposite of the nozzle is the diffuser. You will increase the cross-sectional area until the exit, and the velocity of the exit will be much less than the velocity of the inlet. Okay, so let's draw a nozzle. It is a steady device also. At 200 kilopascal, air enters at 200 kilopascal, so it is P1 equal to 200 kilopascal. Okay, and T1 equal to 65 degrees Celsius or 338 Kelvin. At velocity V1 equal to 35 meter per second. Okay, and exits at B2 95 kilopascal at velocity V2 240 meter per second. The heat loss from the nozzle to the surrounding medium, so we have heat loss Q out, and it is a small qy because he will say it is 3 kilojoule per kilogram, so it is per unit mass, so it is a small q. To the surrounding, the temperature of the environment is 17 degrees Celsius or 290 Kelvin. Okay, find the exit temperature T2 and the exergy destroyed. Okay, the system or the question is in per mass, Q out is in per unit mass, so خلاص the question will continue as per unit mass. X destroyed is equal to 0 unless something is mentioned about rate or anything. So X destroyed per unit mass, so in kilojoule per kilogram. Okay, so how can I find T2? For T2 I have to make an energy balance. Why? For example, this is an air. If I have air or ideal gas, I have two choices. Either I say it is a constant specific heat or variable specific heat, and then use the equation for ideal gases with constant specific heat, or use table A17 with variable specific heat. Okay, I don't have tables for refrigerant or steam to find the temperature. Okay, for the for the temperature, if I made an energy balance, I will say it is En equal to E out. Okay, my last choice is when I have no other option is to use the energy balance. Okay, En equal to E out. I have at the inlet H1, and only H1. I will not multiply by mass. It is in kilojoule per kilogram. That is per unit mass, energy balance per unit mass. I have also kinetic energy per unit mass, V2 over V1 squared over 2. Also, at the exit I will have also H2 plus V2 squared over 2. And I have also the Q loss or heat loss. So it is Q out. Okay. If I have V1 and V2 and Q out is given also, for H1 H2 I can find them either by constant specific heat and say that H1 is equal to CB T1 and H2 is equal to CB T2, but I don't have T2, and already CB, I have to calculate CB at the average temperature T average, okay, which is equal to T2 plus T1 over 2, and I don't have T2. So I cannot use the constant specific heat assumption. I have to use the variable specific heat assumption. Okay. For the variable specific heat assumption, I have T1. Okay. I can use table A17 with T1 to get H. Table A17, you need only one property, so you can get other properties. So I have T1, I can get H1. And from H1, I can get H2 because I have already other things. Okay? From this equation, I can say that H2 after I get H1 is equal to H1 minus Q out plus V1 squared over minus V2 squared over 2, and don't forget to divide by 1000 because to make it in kilojoule per kilogram. Okay, so if I got T1, تمام, 338, I have T1 already. I can get H1, and from H1 I can get H2 from the energy balance, and from H2 I can get T2 also from table A17. If I have H, I can find T. Only one property can give me other properties. Okay, that is for part A. For part B, the Exergy destroyed, X destroyed, I have two ways. One is usually used. It is T naught Sg. Okay, T naught S generation is this one is per unit mass خلاص. Okay, so I will make an entropy balance per unit mass Sn minus S out plus S generation equal to delta S system. It is a steady device, so this one is 0, not change with time. Okay, I have heat transfer by mass m dot, but this in rate, this in per unit mass, so I will not write m, so it is only S1. Okay, also I have S2 as an out, and also I have entropy transfer by heat. Entropy transfer by heat is Q over T, and here I have Q small out over T. T what? T naught. It's the surrounding temperature. يعني you have the nozzle a Q out, that is the system. After the system you have the immediate surrounding, okay, and يعني you have the temperature, and the temperature will be decreased, okay, from the exit to يعني from the turbine until it reaches the environment, okay, like this one. Here I have the system, and it will take some time to reach the environment state, environment temperature T naught. This is immediate surrounding, the surrounding near to the system, and until you reach the temperature of the surrounding. When you reach the temperature of surrounding, then you are in the environment itself. When you reach the environment temperature, then that is the time that you leave the immediate surrounding. Okay. Plus S generation equal to 0. So S generation will equal to S2 minus S1 plus Q out over T naught. Okay, and the Exergy destroyed is equal to T naught S generation, so it is S2 minus S1 plus Q out T naught. Okay, that's the usual one. There is a rarely used one. When you say that you will take the Exergy balance, but not around the system, itself. You will not take Exergy balance here about the system itself. No, you will make Exergy balance around the whole system and the immediate surrounding. So if you say that is the system, that is the nozzle, and here it is the immediate surrounding, okay, and when we reach this red line, it is the environment, okay, like the potato here, okay. I want to take the Exergy balance here at the red line. Why I'm doing this? Because if I take the Exergy balance only around the system, that means there will be a Q out, okay. And for Q out, this will affect my results, okay. And this will affect my results, and I will not get the same value for T naught like T naught is generation. But if I take the whole system and the immediate surrounding together, I can make Exergy balance and get the same value for the Exergy destroyed, okay. So that's other way, but let's stick to what we know. T naught is generation, okay. If you made Exergy balance for this one, xn minus x out, okay, minus x destroyed. I want just to show you that they will be the same at the end by equations, okay. Of course equal to 0 because it is a steady device. xn minus x out, plus this one will be psi 1 minus psi 2, and there will be no heat. The heat is inside my system, my control volume, this red one, okay, minus x destroyed. So x destroyed equal to 0 will equal to psi 1 minus psi 2 flow exergy 1 minus flow exergy 2, and this will equal to h1 minus h2 minus T naught S1 minus S2 plus V1 squared minus V2 squared over 2, okay. This one should equal to the value from this one, okay. How this equation is equal to this equation? So let's put them like this. T naught, or we can say that from the energy balance, if we can use the energy balance, this one, h1 plus v1 squared over 2 equal to h2 plus v squared 2 over plus q out, okay. And we moved everything to the other side except q out. So h1 minus h2 plus v1 squared minus v2 squared over 2 equal to q out, okay. And I said I want to divide the whole equation by T naught, okay, so I can get similar to this equation. And then I want to add plus S2 minus S1, and here I add plus S2 minus S1. I want to get similar to this equation, okay. And then I will multiply by T naught for the whole equation, okay. This will give you at the end T naught S2 minus S1, and this T naught will go with this T naught will give you H1 minus H2 plus V1 squared minus V2 squared over 2, and will give you T naught, this one, Q out over T naught plus S2 minus S1, okay. And T naught S1 minus 1 can be written as negative T naught S1 minus S2. So you can see that this term is the equation from the Exergy balance around the system and the immediate surrounding, okay? But here, that is the equation from T naught S generation, okay? So this one from T naught S generation, okay? From the solution manual, they said he made this, and they said the Exergy Schrödinger process can be determined from an Exergy balance applied on the extended system that includes the device and its immediate surroundings, so that the boundary temperature of the extended system is the environment temperature. Okay, يعني T naught is equal also to the يعني T surrounding، يعني T surrounding اللي هي ال immediate surrounding، يعني اللي هي التمبريتشر اللي هي هنا اللي على اللاين بالظبط، تمام، equal to the temperature اللي بره في ال environment الأساس، يعني زي الرسمة like this photo 25 degrees Celsius is equal to the 25 degrees Celsius of the environment. Okay. Noting that Exergy transfer with heat is 0 when the temperature at the point of transfer is environment temperature. يعني that is why he didn't put Q here يعني because already it is inside the system, and because there will be no heat transfer. يعني if the temperature of the surrounding here is 25 and here it is 25, there will be no temperature difference. Heat moves from high temperature to the low temperature. Okay, so that is other way. But let's stick to our usual way by using this equation. Okay, for this equation I also need to find what S2 and S1. So after I يعني directly from here I need H1, I need also S1. Okay, for the part 2 I need to find S1. Okay, I need to find S1 is equal to what? Okay, and also after I find H2 and I get T2, I also want to find S2. Okay, so let's use the table A17. Table A17. My temperature is 338. Okay, my temperature is 338, and it is between 330 and 340. Okay, so let's make energy balance interpolation. Okay, so we'll make interpolation between T and H, so I can get H, and also I want to get S. Okay, my temperature is between 330 and 340. So 330, my temperature is 338, and the highest temperature is 340. That is 330.34. H1, and this one is 340.42. And for S, it is 1.71865 if you see the table, and this one is what I need to find the I am getting now S naught. Okay, so S2 and S1 can be found from the equation for the variable specific heat. S2 minus S1 is equal to what? S2 naught, yep, minus S1 naught minus R ln B2 over B1. Okay. Okay, so for S1 naught and S2 naught, this is the wrong one. For S1 naught it is 1.79783, and this one is S1 naught 1.8279. And for second state, I need to get the enthalpy, then I can find H2. So we'll make the interpolation 338 minus 330 over 340 minus 330, and equal to S1 naught minus 1.79783, 1.8279 minus 1.79783, and this will equal to, for the enthalpy also, is H1 minus 330.34 over 40.42 minus 330.34, and H1 will be 338.4 kilojoule per kilogram, and S1 naught is what? S1 naught is 1.8219 kilojoule per kilogram Kelvin. Okay. So I have H1, then I can use the energy balance to get H2. So H1 is equal to 338.4 minus 3 the Q out plus 35 squared minus 240. You can see V2 is much higher than 35, so that is the function of the nozzle, divided by 2, and we have to multiply by 1000, so we can, to make it in kilojoule per kilogram, and then H2 will be 307.21 kilojoule per kilogram. So that's the H2, and I will use this value for H2 to get T2, the part A, the required in part A, and to get also S2. So from H2, 307.21 kilojoule per kilogram will give you from the table. I have to go to the table. 307.1. 307.1 is between 3.05.22 and 310.24. Then I want to get the temperature between 305 and 310, and S naught between these two numbers. Okay, so also I need to make interpolation. So interpolation between H, T, S. Okay, so for H2 5.22, my H2 is 307.21, the highest enthalpy is 310.24. The corresponding temperatures are 305, T2, I want to find T2, and 310 for the entropy, 1.71865, and this is not yani. I want to find S2 naught, and this one is 1.73498. The corresponding to yani these two numbers are corresponding to the enthalpy and temperature. Okay, this two. This will give me 0.72.21, that's my enthalpy, minus 305.22 over 310.24 minus 305.22 equal to S2 naught minus 1.71865 over 1.73498 minus 1.71865. Okay, that is for entropy. For enthalpy, it will or for temperature, T2 minus 305 over 310 minus 305. T2 will be equal to 307 Kelvin, and it is equal to 34 degrees Celsius. And for S2 naught, it will be 1.7251 kilojoule per kilogram Kelvin. And okay, we find part A, T2. So we want to find the Exergy destroyed, so we'll use the equation for the Exergy destroyed, this one. Okay, but before we have to find S2 minus S1. So S2 minus S1 is equal to 1.7 251, that's S2 naught, minus 1.8219, minus the idle gas for air from table A1, okay, 0.287, 0.287, then the pressure 95 kilopascal and 200 kilopascal. This will give you S2 minus S1 is 0.1169 kilojoule per kilogram Kelvin. Okay, for the Exergy destroyed, finally, it is this equation. Okay, it is S2 minus S1 is okay. First, T naught is 290 times S2 minus S1 is 0.1169 plus Q out is 3 given the question over T naught is 290. So this will give me Exergy destroyed equal to 36.9. يعني regarding what we did at the two ways, يعني this one is Q out over T naught. Why T naught? يعني at the beginning it wasn't T naught. At the beginning it was a temperature in the surrounding. It goes out from the nozzle to a temperature. We don't know the temperature, but we know the temperature of the surrounding or the environment. The temperature of the environment and the immediate surrounding are the same at this point. At you can say the point that they meet, the temperature will be the same for the immediate surrounding and the environment. Okay, that is why I put here T naught. Okay, Q out over T naught. So for doing this, I cannot do this if I take the Exergy balance around only the system. I will not reach this point. Okay, so that is why we made it around the whole system that include the system itself is the air and the immediate surrounding. So we can have T naught يعني, or we have Q out when it reaches this one, and when it reaches this one it will be 0. Why? Because nothing will be transferred more than this point, because this point, يعني, for example, this the temperature surrounding is 290 Kelvin. At this point, it's also 290 Kelvin. So there will be no heat transfer at this from here to here. يعني خلاص, يعني heat transfer is between a high temperature to a low temperature. That is why we included the immediate surrounding, and we didn't make the Exergy balance is only about the system or the air only. Okay. That is for this question. It was a very long question. Okay, still we have other two questions, inshallah, and we will finish this video. Okay, for question 855. 855. Now we have a diffuser. Diffuser, it is the opposite of nozzle, so you will have a higher or a bigger cross-section area at the exit, so the velocity will be less at the exit. Okay, steam, we have steam, so I can use table A4 to A6. A diffuser at 10 kilopascal enters at 10 kilopascal, so P1 is 10 kilopascal, and T1 is 60 degrees Celsius or 333 Kelvin. Okay, with a velocity V1 equal to 375 meter per second, and exits at as a saturated vapor. Okay, at T2 equal to 50 degrees Celsius or 323 Kelvin, with V2 70 meter per second. Okay, the exit area, so A2 or A exit يعني, is 3 meter per meter squared. Determine the mass flow rate, so m dot in part A of the steam, and the wasted work potential. Wasted work potential, irreversibility x destroyed يعني. Okay, x destroyed. And this يعني he wants for me to find the mass flow rate. خلاص يعني of course I will use it x dot destroyed. Wasted work potential يعني can find it from the definition of the Exergy destroyed. Exergy destroyed represents the lost work potential and is also called irreversibility or lost work. Okay, so lost in work potential or the wasted work. Okay, if you find the irreversibility also called Exergy destruction or lost work, which is the wasted work potential during a process because of irreversibility. Okay, so that is X destroyed in rate form. Okay, kilojoule per second, kilowatt يعني. So how can I find the mass? I said to you before, if you have area, so usually you will have to find the mass flow rate. So the mass flow rate, we know it is the volume flow rate over the specific volume, and it is area times the velocity, that is velocity, okay, over a specific volume. I have the area of the second, I have the velocity of the exit, so I have to get the specific volume at the exit, okay. That is for the part A. Okay, for part B, X destroyed, you say خلاص the easiest way is to use X destroyed equal to T naught S dot generation, because it is a rate. I will make the entropy balance in rate S dot N minus S dot out plus S dot generation equal to delta dot delta S dot system. Okay, this one is 0 because it is a steady device, not change with time inside the diffuser. Okay, he didn't say it is adiabatic. Okay, so I have a heat transfer, even if he didn't say the previous question he mentioned the value, but here he didn't say it is adiabatic, so I will assume there is heat transfer also. Okay, I have entropy transfer by mass, so it is m dot s1 minus m dot s2, and why it is يعني why I will now put يعني q dot out, not why I didn't put q dot in, because usually there is a heat loss, not heat in. From where it will come heat in? يعني heat in يعني you produce this heat. There is no boiler, there is no heating, there is no anything that mentioned or device that mentioned about heating. Okay, but usually without doing SN you are losing heat loss because of the irreversibilities. Okay, because there is friction between the layers of the steam with itself, or the steam and the diffuser. Okay, there is irreversibilities. That's why there will be a heat loss. Okay, and heat loss will go out because of the temperature difference. So this is also a type of irreversibility. Okay, Q dot out over T naught. I assume it is. I calculate when it is at the immediate, يعني the line between the immediate surrounding and what the environment. Okay, so like the previous question, that's the diffuser. Around the diffuser there is the immediate surrounding. Okay, I'm calculating at this point. Here is the environment. Okay, I'm calculating here the immediate surrounding. Okay, and here's the environment. I'm calculating at this point. يعني the heat will go out and will move in different temperature, from high temperature to low temperature to high temperature to low temperature, until it reaches the environment temperature. When it reaches the environment temperature, it will not continue. There will be no heat here. Okay, that's why I'm saying q dot out over T naught. Okay, plus S dot generation equal to 0. So S generation is dot generation will equal to m dot S2 minus S1 plus q dot out over T naught. Okay, and for the Exergy destroyed, I will multiply by T naught, S dot generation times T naught, and I will get this value. S2 and S1 I have to get it also from the steam tables. Okay, so I need S2, S1, V2 because I want to find the mass flow rate. Okay, what about Q out? Q dot out, I don't have the value. In the previous question, I have the value of the Q. Here, I don't have the Q dot out. Okay, so in the previous question, from where where did we use the Q dot out? We use it in the energy balance. So here also we will make energy balance. Okay. Directly in equal to out, it is steady device, not change with time. Okay, and it is in rate form, it is E dot. Okay, I have M dot H1, the inlet of the user. I have energy. Okay, internal energy and flow energy, and they represented in the H1, the enthalpy. I have kinetic energy, M dot V1 squared over 2. Of course, the mass of the inlet is the same as the exit, so it is only mass flow rate. Equal to M dot H2 plus V2 squared over 2 multiply my mass flow rate, and we have the Q out, Q dot out. Okay, I have the velocities. I have to get the mass if I get the specific volume. Also the enthalpies. I have to get the enthalpies. I have to get H1, H2. Okay, that is it. So if I get Q dot this properties, I can calculate Q dot out, and then I can calculate X destroyed. Okay, so Q dot out will be equal to M dot H1 minus H2 plus V1 squared minus V2 squared over 2, and we will divide by 1000 when we want to substitute, inshallah. Okay, let's find the properties from the thermodynamics table. Okay, for state 1, I have P1 equal to 10 kilopascal, okay, and equal to 0.01 megapascal, and T1 is equal to 60 degrees Celsius. Okay, and I want to find H1. I want to find also S1. Okay, I don't need anything else than H1 and S1. For state 2, I know it is 50 degrees Celsius, the temperature, and I know it is saturated vapor. So the quality is equal to 1, and I have to find everything at G. Okay, I need H2, and it's equal to Hg, and I need S2 equal to Sg, and I need V2 because I want to calculate the mass flow rate, so it is Vg also. And that is it. Okay, so let's find from the table. I will go for the steam table. Table A5. Okay, 10 kilopascal. Okay, and my temperature is 60. 60 is higher than saturation temperature, so it is a superheated state. Okay, so I will say that T1 is higher than Tsat. Okay, and it is 60. Of course, the higher the temperature, the most probably the chance that you will be a superheated state. Okay, from table A5, the pressure table. Okay, the degrees Celsius is higher than 45.81 degrees Celsius, and it is a superheated state. Okay, so I have to go to the superheated table A6. Okay, at 0.01 megapascal. 10 kilopascal, 0.01 megapascal is equal to 10 kilopascal. So 0.01 megapascal, you divide by 1000. At 60, and I don't have 60, I should make interpolation. Okay, and to find H and S between 50 and 100, and these two values for H and these two values for S. Okay, so let's make interpolation. Okay, interpolation between T, H, and S. T is 50 My temperature T1 is 60, the higher temperature is 100, 2592. I want to find H1, 2687.5, 8.1741. I want to find S1, 8.4489. Let's make the interpolation. 60 minus 50 over 100 minus 50 equal to H1 minus 2592 over 2687.5 minus 2592. This also will equal for the entropy S1 minus 8.1741 over 8.4489 minus 8.1741. Okay, this will give me H1 is equal to 2611.1 kilojoule per kilogram, and I think for the solution I got it 2612, and in each state it will be different until we reach the final part or final requirement, and there will be a 20 kilowatt difference between my answer and the solution manual answer, because I think he used a different thermodynamic table or a new edition. Okay, kilojoule per kilogram, and S1 is 8.229 kilojoule per kilogram Kelvin. Okay, that is for state 1. So I got H1 2611.1 kilojoule per kilogram, and I got S1 is 8.229 kilojoule per kilogram Kelvin. Okay, for state 2, I have only temperature, so I will go to table A4, the temperature table, 50 degrees Celsius. Okay, this one, and he said saturated vapor, so I get G, VG, HG, and SG. Okay, this will equal to H2 equal to HG equal to 2591.3 kilojoule per kilogram. SG is 8.0748 kilojoule per kilogram Kelvin, and for the specific volume 12.026 meter cubed per kilogram. Okay, now I got everything. Let's substitute in our equations. So for the mass, I will use this equation. Okay, so the area is given in the question 3, the velocity is 70, the specific volume we got it from the table 12.026 will give us 17.46 kilojoule per second. Okay, for Q dot out, because I want to find Exergy destroyed and I need Q dot out, it will be N dot is 17.46, H1 minus H2 is 2611.1 minus 2591.3 plus V1 squared is 375 squared minus, don't forget the bracket, and don't forget to divide by 1000. Okay, and this will give you Q dot out equal to 1531 kilojoule per second. Okay, or kilowatt, yeah. Okay, kilo is small k. For the Exergy destroyed, that is its generation. So Exergy destroyed, X dot destroyed is equal to T naught. S generation is M dot S2 minus S1 plus Q dot out over T naught. Okay, and this is equal to 198, 17.46, 2.0748 minus 8.229 plus 1531 over 298, and this will give you X destroyed is equal to 7 to 8.7 kilowatts, okay, or kilojoule per second. And if we made our Exergy balance around the whole system and the immediate surrounding, okay, and you will make it here, okay, we will get the same value for the Exergy destroyed, okay. So you can say x dot n minus x dot out minus x dot destroyed is equal to delta x dot system, and this one is 0, and we have our diffuser, and that is the immediate surrounding, and here it is the environment, okay, here is the immediate surrounding. I will take my control volume, or I will make a Exergy balance at this line where the temperature of the immediate surrounding is the same as the temperature of the environment, which is T naught, okay. So I will ignore the heat because the heat is here, and heat will not go after it reaches the temperature T naught, because if it reaches the temperature T naught and here is also T naught, so how it can move? The Q is moving from a high temperature to a low temperature. If they are the same, it will not move. There will be no heat transfer. So at this point, heat transfer is 0. Okay, that is why if I take at this line or at this control volume, I will not include Exergy transfer by heat transfer 1 minus T over T Q, because if you say 1 minus T naught over T, TK QK يعني أو Q dot K أيا كان تمام. TK it will be equal to T naught at this point. K means the location of the heat transfer, or the temperature of heat transfer. Okay, TK will equal to T naught, so this one will be also equal to T naught. T naught over T naught is 1, 1 is 1 is 0, so this term will be 0. That is why I will not include this in the Exergy balance when I take the Exergy balance around the system and the immediate surrounding. Okay, okay. This will give you m dot phi 1 minus m dot phi 2 psi 2, okay, and x dot destroyed, okay, equal to 0. This will give you at the end x destroyed is equal to m dot 1 minus 2, and from the long equation m dot is equal to h1 minus h2 minus t naught s1 minus s2 plus v1 squared minus v2 squared over 2, and don't forget to divide by 1000. Okay, this will give you 17.46, that is the mass flow rate. H1 is 2611.1 minus 2591.3 minus T naught 298, 8.229 minus 8.0748. That is the entropy change. Okay, plus 375, that is V1, and look, V2 will be much less than V1 because it is the diffuser. It will decrease the velocity. Don't forget the small bracket, and don't forget to divide by 1000. Okay, this will give you x destroyed, also the same number that we got before, 728.3 kilojoule per second. It was 0.7, so it doesn't matter, and not a big difference. Okay, that's the value. So that is for this question. Let's go for the last question, and it is a question that came before in previous exam. Okay, let's see the last question. Okay, 871. Finally, he drew the nozzle. Okay, we have hot combustion gases, and we faced combustion gases before, and we know that combustion gases do not have any tables, so we know the trick that we will get R from CB minus CV, and we don't know CV. He already gave me only CB, and then we will say CB is equal minus CV, which is K is equal to CB over CV. So CV is CB over K, and then we will take the CB as a common factor. So this trick came before in the question and the exam. This will be 1 over K, and then we get R. Okay. But let's see the question how we will solve it. Hot combustion gases, we will treat them as ideal gases. Ideal gases. Okay. Enter the nozzle of a turbojet engine at 230, so this B1. T1 is 627 degrees Celsius and equal to 900 Kelvin. Okay, and velocity V1 is equal to 60 meter per second. And at exit equal to B2 equal to 70 kilopascal, and T2 is 450 degrees Celsius, or in Kelvin 723 Kelvin. Okay, assuming the nozzle to be adiabatic. Okay, now we have a question with adiabatic nozzle or diffuser. Now it is nozzle, adiabatic nozzle, so there is no heat transfer. In the previous two questions there was heat transfer. Okay, the surrounding temperature T0 is 20 degrees Celsius or 293 Kelvin. Determine the exit velocity. So he wants for me to find V2. And for part B, the decrease in exergy. Decrease or increase means change يعني in exergy. So he mean delta X, or for open system we say it is phi minus phi. So يعني either phi 1 minus phi 2, it will give you psi 1 minus psi 2 exergy flow minus exergy 2 flow exergy at state 2. This value will give you positive. If you put x2 minus psi 2 minus psi 1, this will give you negative, because he says it is decreased. So 1 was higher, then it decreased. Okay, this will give you a positive number, this will give you a negative number. The same number it will be at the end. Okay, but yani we want to find everything in a positive number. He wants about the decrease. We know it is a decrease, so no need for the negative number. So I want to find psi 1 minus psi 2, or flow exergy 1 minus flow exergy 2 in the second part. Okay, in the previous two questions, one time he wanted for me to find T1, and the other one he wanted for me to find mass flow rate, and this one he wanted to find V1. In the previous two questions we used energy balance. Here also we'll use energy balance. So let's make energy balance En dot equal to E dot out. Okay, I have enthalpy M dot H1 plus kinetic energy M dot V1 squared over 2 equal to M dot H2 plus M dot V2 squared, and I don't have any heat transfer, so, and I don't have work. It is not like compressor or turbines. We have I don't have work, so that is the energy balance. Okay, I want to find V2. Okay, I don't have the mass flow rate in the question. Okay, and he didn't give me volume flow rate, so I can divide. He didn't give me area, so I can use it. He didn't give me anything that I can use it to find mass flow rate. So, and already we said in part B we will assume it is خلاص, يعني it is per unit mass, يعني always psi or flow exergy is per unit mass, kilojoule per kilogram. So let's divide the whole equation by mass. So from the beginning, يعني no need to write this one. I should have been wrote يعني this En equal to E out directly. If I divide it by mass, so it will give me H1 plus V1 square over 2 equal to H2 plus V2 squared over 2. Okay, and I want V2, so let's multiply by 2, so it will give me 2 H1, and before this one, let's move H2 to the next side, so it will be H1 minus H2 plus V1 squared over 2 equal to V2 squared over 2. Let's multiply by 2, so it will be 2 H1 minus H2 plus V1 squared over 2 equal to V2 squared. Okay, let's distribute the 2. It will be 2, and I want to make H1 minus H2 alone, because I want to make a constant specific heat. I will assume it is a constant specific heat. We have combustion gases, either I say variable or constant specific heat, but here he gave me in the question C, B, and K. So I am forced to use constant specific heat, because variable specific heat we don't use CB or K or CV, only in constant specific heat. Okay, so I will assume it is a constant specific heat. Okay, so I can say at the end H1 minus H2 is CB delta T. Okay, and then I will distribute 2 on the kinetic energy, will give me only V1 squared, and this will also equal to V2 squared. Then I will take the square root. This will give me V2, then it's equal to 2 H1 minus H2 plus V1 squared. Okay, and we said it's a constant specific heat, so H1 minus H2 is CB T1 minus T2. Okay, so V2 is equal also T 2 CB T1 minus T2 plus V1 squared over 2. So V2 is equal, I have CB, I have the temperatures, I have the initial velocity, so I can get V2 directly. Okay, 2 CB is given 1.15627 minus 450. Okay, plus 60 squared. This one is in kilojoule per kilogram. It is enthalpies. This one is meter squared per second squared. I mean, meters over second, the velocity squared will be meter squared over second squared. So they have different interpolation. Different in units. Okay. I usually said when you have velocity divided by 1000, because we want what? We want exergy, we want work, so we want in kilojoule per kilogram. Here we want the opposite. We want the velocity. So I will multiply by 1000. Okay. We know that the conversion factor is 1 kilojoule per kilogram is equal to 1000 meters squared over second square. So this in kilojoule per kilogram. So I will multiply by 1000 meters squared over second squared. Okay, and here is 1 kilojoule per kilogram. So I can they will cancel each other, and the remaining is meter squared over second square, and this one is meter squared over second square. So V2 at the end will give me 641 meter per second. So be careful to do not forget to multiply by 1000. Okay. For the second part, we say that we want the exergy change, or the decrease in exergy, psi1 minus psi2, and this have its equation H1 minus H2 minus T naught, and this is negative T naught. Okay, because in the equation sheet this one is wrong. Okay, this one is wrong. If psi2 minus psi1, psi minus psi2, all this is negative. Okay. And you say negative T naught is 2 minus S1. Okay, if this one is psi1 minus psi2, it will be negative T naught S1 minus S2. So there is a mistake in this equation. This should be a negative one. Okay, so tell the doctor to change this one. Okay, this one is negative. Okay, and all the previous one are negative already. Okay, this one is negative. Okay. Minus T naught S1 minus S2 plus V1 squared minus V2 squared over 2. H1 minus H2, we know it is CB delta T, okay. For S1 minus S2, we assume it is a constant specific heat, so we'll use the constant specific heat, S1 minus S2. The equation is CB ln T1 over T2 minus R ln B1 over B2, and we know that R, I don't have any table for the combustion gases, so I have to use the trick that we talked about at the beginning of the question and in the previous questions. So R is equal to CB minus CV, and K is equal to CB over CV. So R is equal to CB minus CB over CV, and if we take it as a common factor, the constant specific heat, that constant pressure, it will give me 1 over this one, this K, this one is K, okay, over K. And then CB, R is equal to CB is what? Is 1.15, 1 minus 1 over K is 1.3. This will give you R is 0.2654 kilojoule per kilogram Kelvin, the unit of the specific entropy. So for S1 minus S2, S1 minus S2, CB is 1.15 ln T1. So look, here is 1, we wrote 1 first. If we wrote 2 first, this will be 2. So be careful. Okay. Ln T1 should be in Kelvin, so it is 900 over 723 T2 minus R 0.2654. Ln B2 is 230 over 70. Okay, kiloscale. So S1 minus S2 is equal to negative 0.6388 kilojoule per kilogram Kelvin. Okay, so we got everything. So let's substitute in this equation. Okay, so psi 1 minus psi 2, Exergy flow 1 minus Exergy flow 2 is equal to H1. H1 is H1 minus 2 is CB delta T, so it is 1.15 CB. T1 is 900, T2 is 723 Kelvin. Kelvin or Celsius? If they are both Kelvin, okay. They are both Celsius, okay. But don't mix. One is Kelvin, one is Celsius. I put in Kelvin. Okay, nice. Okay. Minus the T naught is 293. The S1 minus S naught is negative 0.06388, and for the velocity, V1 squared is 60 squared minus 641 squared. We got it in the part A, and over 2. Don't forget to divide by 1000. Okay. I already didn't put a bigger bracket, so no need. Okay, and psi 1 minus psi 2 will equal to 18.6 kilojoule per kilogram. And by this question, we finished our video about nozzles and diffusers. Maybe we'll have a last video, inshallah, about throttling valve, mixing chamber, and heat exchanger, inshallah. I will solve only one question on each of them. The throttling valve is a very short question, but the other two are too long. And they have more than single stream. There is no only one inlet and one outlet. There will be more than inlet or more than outlet. Okay, so thank you for your listening.